Last class, we started talking about what normal distributions were and how to calculate the distance a given data value is from the mean. Today, we're going to want to talk about how the distance from the mean affects the probability of something happening again. So, when I'm analyzing data, the main question is, what is the chance of this happening again? So if I get all 80s and above on civics tests, what's the probability that I'm going to earn a 90%? So the way we do this is the most basic ways we use what's called the empirical rule. The empirical rule is also known as the 68, 95, 99.7 rule. What that means is, sorry, can't use this, as it says 68% of data falls within within the first standard deviation. 95% of data falls within the first two standard deviation, and 99.7% of data falls within the first three standard deviations. So 99.7%, that's really close to 100%. So idealistically, in my bell curve, 100% of my data is underneath the bell curve. So if I go through and I draw this out and I label our bell curve, remember our mean always goes in the middle. And then I have three standard deviations above the mean, 1, 2, and 3. And then I have three standard deviations below the mean. So -1 sigma, -2 sigma, -3 sigma. So since 68% of my data falls within the first standard deviations, so that's the first to the left and the first to the right. This all here, and if I make that bigger so we're not here all day, this value right here, 68% of your data falls within right here, which makes sense because that's the biggest portion of your bell curve. That's the biggest area. So it makes sense that that is going to make me the vast majority of your data. Then it says 95% of your data falls within the first two standard deviations. So that's everywhere that I just highlighted. That's 95%. And if I just come up this way, that's 95% of my data. So 95% of my data is where the most area of your bell curve is. And then 99.7% of your data is almost the whole thing except for the wings. So it's everything that's three standard deviations away. That's 99.7% of my data. So notice that's not 100%, but that's very close because there is still some probability of getting into those wings. So how do I find the probability of what's left over? Well, 100 minus 99.7, that equals 0.3. So this wing plus this wing make 0.3% of your data. So how I figure out what each of those wings are is I just do 0.3 divided by 2, which is 0.15. So 0.15% of your data falls there, and 0.15% of your data falls on the left wing. Now remember we always told you the further away from your standard deviation, the less likely it will occur. Well, that's exactly right, because you have a 0.15% that's a percent chance of being able to fit in there, which that's a very rare chance. It could still happen, but it's pretty rare. So let's go through and let's check this example. It says on the last civics test, student scores represented a normal curve. After analyzing the test results, we found that X is approximately normal with a mean of 80 and a standard deviation of 5. Remember, this first number is the mean, second number is standard deviation. So I'm going to go ahead and draw my bell curve because that always helps me. Whenever I get stuck on a problem, even if it doesn't have a bell curve, I usually draw one just to help me. So 80 goes there, and now 85 goes there, 90 goes there, 95 goes there. 75 goes there, 70 goes there, and 65 goes there. So now, it says 68% of my students score between what? Well, 68% is between the first two standard deviations. So what's the first two standard deviations? That's between 75 and 85. So we write this in interval notation, where we just write 75, 85. So that just means between 75 and 85 is where 68% of your students fall. What about 95%? Well, 95% is 2 standard deviations. So I go 2 standard deviations, 2 standard deviations. That's between 70 and 90. And if we do 99.7, that's 3 standard deviations, which is between 65 and 90. So in this specific set, in this specific example, 99.7% of students got between a 65% and a, not 90%, how about a 95%, 3 standard deviations. So the nice thing about the empirical rule is we can break it down a little bit further. So we don't always have to just say 68, 95, or 99.7. So if I draw, again, and I just label my picture generically, here's my mean, 1 sigma, 2 sigma, 3 sigma, negative 1 sigma, negative 2 sigma, negative 3 sigma. I know that between 1 standard deviation is 68%, right? But how do I figure out what half of that is? How would I want to know what the area of just what I shaded right there? Well, I would just do 68. I would just do 68 divided by 2, which is 34. So that's 34%, and that's 34%. All right. So now, what if I wanted to find the area of this little wing right here? Well, I know this whole thing makes 95, and if I take out the gray area, I would do 95 minus 68, which is 27. So both of these blue areas are 27%, but how you find what one of those areas are is you just divide by 2. So you get 13.5% in each piece. So now what if I wanted to find this itty bitty wing? Well, I know this whole thing is 99.7. So to find the wings, I could subtract 99.7 minus 95, because that's everything in the middle. I get 4.7, and then if I divide by 2, I have 2.35. So that will be 2.35% and 2.35%. And then we figured out how to get the wings past 3 standard deviations. We did that above up here. And that was 0.15% and 0.15%. Notice the further away you go from the mean, the smaller the probability, the smaller the chance that that will occur. So now let's go ahead and let's answer these questions based on the problem above. It says, what percent of students scored between an 85 and a 90%? So if I go back up to this picture, 85 and 90% is 1 sigma and 2 sigma away. So now if I come back to this graph, 1 sigma and 2 sigma is 13.5%. if I look at the next one, what percent of students scored below a 75%? So 75% is here, everywhere below it. So that's 1 standard deviation and below. So that's here and everywhere below. So I would just add up 0.15 plus 2.35 plus 13.5, and I get 16%. So what this means is I have a 16% chance of a student scoring below a 75 on this test. Not a very big chance, so fortunately that's pretty decent. Last one. What is the percentage a student needs to be score higher than a student scores higher than an 85? So 85 is there, all the way up. That's 1 standard deviation and everywhere above. So I would add 13.5 plus 2.35 plus 0.15. I get 16% again. So again, that means I have a 16% chance of somebody scoring, of the class scoring above an 85%. So again, that's not great, but still an 85 is a pretty awesome grade, so that's pretty good from where we are. So go ahead and flip your paper. Let's go back and look at our Skittles. These were the numbers of Skittles that we all calculated last class for each of your fun-sized bags. It says, remember that this data was approximately normal with a mean of 43 and a standard deviation of 43. So it says label the bell curve. So I did a really awesome job, and I forgot to import a bell curve into this graph, into this worksheet, but that's no big deal because I'm just going to squeeze it in up top here. I recommend writing it pretty big so you can see it. But it's always good practice to draw these because, again, not always are you going to be given a bell curve, and sometimes my advice is to just draw one when you get stumped. So 43 goes in the middle, and then I keep adding 3. 46, 49, 51, 40, 37, 34. It's hopefully you're all okay with that. I'm going to keep going. Then graph a dot for each of the if I can speak coherent English, graph a dot for each bag on the number line above, represented by the number of Skittles it contains. So 46, I'm going to go and I'm going to plot them in red, actually. 46, I'm going to go over, and 46 would fall right there, so I'm going to plot a dot. 44 would be right here next to 43, plot a dot. I'm just going to cross them out as I use it. There's another 44, cross it out. I now have 40, and then I have 48. So go ahead and you pause this video and you finish, and then all the answers will be up here. But you don't need to watch me, and I don't need to waste time doing this. So notice all my bags are plotted with red dots and the number of candies each of you had. Notice everybody's number of Skittles all is underneath my bell curve. So it says, what percent of our bags of Skittles are represented on this graph? Well, 100%, because all of it's under there. So now I'm going to show you, let's go ahead and let's look at this. I want to find the range. It says number of bags in this range. So how many red dots are between 40 and 46? We're going to include 40 and 46. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I had 16 between 40 and 46. Let's just go through and fill out the rest of the table. What about 37 to 49? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22 for the last range. So now it says percent of bags. So how I do that is I do 16 divided by the total of bags in this problem. So total of bags, there were 22. I think I forgot somebody's, but we'll just use what I have. 16 divided by 22 is 73%. 21 divided by 22, 95%. And 22 divided by 22 is 100%. What do you notice? Well, I notice that these values are pretty close to the empirical rule. 68, that's pretty close to 68. 95, 99.7. 1 standard deviation, 2 standard deviation, 3 standard deviation. So what do I notice? This is close to 68, 95, 99.7 rule. So it does work no matter what the data that we're given. So go ahead, and this practice problem you're going to complete on your own, and then I will check that it's completed next class. If you have questions, make sure you come and see me.